Good afternoon, everybody. My name is Hannu Juola. I'm from the University of Oulu in Finland, and I'm here to share with you our findings on adaptive geological uncertainty modeling in excavation. Our research was funded by Business Finland grant as a part of our SWARM project. And we looked at how we can transition from reactive to proactive earthworks construction, as preliminary information for earthworks is usually gathered through ground mapping, such as soundings, boreholes, or soil samples to create an understanding of the prevailing soil conditions of a project area. And with this information, nowadays, earthwork processes and information models are created. And what we saw in our studies is that there's a lack of flexibility to create adaptive models for implementation when applying this preliminary information with finite element method calculations. And what we saw is that there is a need for less intricate and not so calculation heavy modeling tools to be implemented into the construction works as they are done today. And from this, we studied the potential of adaptive geological information derived during excavation by looking at the effects of incorporating new information into a geological uncertainty model during the excavation process itself, and thus creating a geological model for entire project areas with verified soil boundaries of partial areas only. And the uncertainty model that we used in our study is part of the Tyrant's GeoPIM concept implemented in Sweden, which determines the geological boundaries based on cracking interpolation and Bayesian statistics. And the uncertainty model itself is performed by a Python code running on a server and controlled by the end user itself on the Microsoft Teams platform, which is a very important part in our study for the fact that it helps end users to use it as they don't have to learn a new program. They can use something that's already familiar for them. And the previous studies on this uncertainty model had a one-step verification. So they checked their calculations and results by the uncovered final excavated ground. But as we, in our study, introduced new information into the algorithm whilst excavating, we also introduced a three-step verification process. So we did have additional soundings points which were not in the initial model. Then secondly, we checked the verified true soil boundaries with soil samples. And thirdly, we checked the final results with the uncovered ground after the excavation had been completed. And what this uncertainty model produces for the end user is a two-dimensional map of the uncertainties, the uncertainty level of the project area. Secondly, you can export solids out of the model. And thirdly, and most importantly, you can export boundary meshes, for example, in land XML form, which then you can use in other information modeling products which are widely in use nowadays. We tested our theory with two types of scenarios. First one is a quite traditional systematic excavation, which we had from the western boundary to the east boundary of our project area. And the second one is that we tested it by excavating from the most uncertain area of that project outwards. And we fed the information whilst excavating into the uncertainty modeling program in 20% increments while excavating. And the results that we received from there is that, well, firstly, the the second scenario, where we are excavating from the most uncertain area outwards, produces much faster, more precise information about the soil boundary, the true soil boundary, when it's estimating it while going forward. But also so that the inside the first 20% of excavation, the largest development in the uncertainty model happens, especially in the second scenario, where the uncertainty decreased by a total of 35%. And when the excavation continues onwards, after 60% of the ground was uncovered, the uncertainty in the second scenario was only 15% at that time for the rest of the excavation ground when interpreting it, compared to the first one where it's still at 30%. So there's a 65% difference between these two at that point already. It's pretty well shown as well in this kind of a chart form. You can see how quickly the second scenario starts equalizing itself, especially in the last 40% of the excavation. So you can see in this chart that with 0% of the excavation completed, that's what majority of groundworks nowadays uses as its information. And our conclusions in our study, well, firstly, we saw that the results derived in our test site data indicate that adaptive updates can significantly reduce the uncertainty of earthworks. And with that, we can minimize the amount of surprises that happen during the earthwork processes. Secondly, the uncertainty models can potentially lead to precise boundary-based autonomous excavation, with the models dictating how the excavation adapts to changes in soil boundaries while it's in progress. And our proposed adaptive uncertainty model can create a tool that enables autonomous excavators to excavate with precision, where previous machine control models have been more robust in their definition, because they have directly interpolated between the points of initial information that they have received from the ground that they're mapping. Additional to the benefits that we can get from autonomous excavation in the future, this tool can provide a lot of new positive impacts for contractors, as using this model with the information that they have from the during their progress, they can get more precise and effective tendering offers, timetabling, logistics, and mission calculations of their the ground that they are going to be excavating. And we see that the further development of the algorithm depends on the operational experience derived during field tests. And that's why we suggest that the ground condition database should be made up for this, which can significantly advance the algorithm's development in the future. And after saying all of this, this does not exclude the fact that you need proper and thoroughly done ground mapping as initial information, because the quality of those soundings or boreholes that you do in the beginning is crucial on how well the uncertainty modeling will be done in the future. I'd like to thank Dr. Mats Svensson and his team at Durance for me being able to use their model in my studies. Thank you.